Hey guys, welcome back. So we're going to do a quick review today. Should be a short video, nothing new. Just going over some of the basic methods that we have for inferences with means. So I'll try to keep this short. I'm sure you guys saw the announcement. So just a quick change in the policy. I am going to be looking at your homework. So if you'll be uploading that to the Google Classroom, I'll be contacting parents if you guys are not doing any of the assignments, just so that they know what's going on and what they expect of you, and we're just clear on that whole thing. So especially if you guys are taking the AP test, we really need to make sure we get through this last unit. That's why I'm going through all of this. It's a lot of work on my end, and if only a few people are watching the videos, it kind of demotivates me to put these things out each day. So let's just do the right thing, and I'll make sure I hold you guys accountable by contacting your parents if you guys aren't actually doing the homework. So getting right into it, there was this is an example from the book. A concerned citizen was concerned that people were speeding through his neighborhood where the speed limit was 30 miles an hour. And so he saw there was a speed trap or a radar that was set up to tell people their speed and the speed limit, and it flashes at them. I'm sure you've seen something like that when you're driving. There's one right by where I live as well. And every time I drive by it, I always drive under the speed limit, slow down so that it's not blinking at me. And then as soon as I drive past it, I go back to my previous speed, which is, anyway, I plead the fifth, so I'm not going to tell you. Anyway, you'll have to catch me in the act. But anyway, speeding's not a good idea. And you guys, traffic accidents, I think, is the number 2 cause of death among teenagers, right after Tide Pods. Yeah, so don't quote me on that one. All right, so anyway, be safe out there. So speed limit is 30 miles an hour. In case you're wondering, this is like epic Photoshop. Yeah, it just looks so much better. You didn't even know unless I pointed it out to you. So anyway, he looked at the speed trap for about 15 minutes, and he clocked all the speeds of the cars that went through his neighborhood. And he collected that data as a sample, and he wanted to see what was the average speed of the cars that were going through his neighborhood. Was the average above the 30-mile-an-hour speed limit? Then he'd be able to say, on average, people were speeding and not respecting the speed limit through his neighborhood, which was his concern in the first place. So a concerned citizen sampled 23 cars in 15 minutes. So the first thing, was this a random sample? Can we expect it to be representative of all the cars that drive through the area? And randomization is also tied to independence, because if it's truly a random sample, then each one will also, individual datum will be independent of the next one. So was it random? No, it was a convenient sample. There was no method to do a random sample throughout the day or certain days of the week. And so it just depends on the time of day. I mean, if he looked at the people going through his neighborhood right after the schools let out, people probably going to younger people probably going to be speeding through there. But if it was like 7 o'clock in the morning, when grandma's going out to get groceries, back when grandmas used to leave their houses, I know this is so sad, then the speed limit, they're probably going to be going under the speed limit, right? So the time of day would probably determine the speed that people are going to be going. So this is not a random sample, it's a convenient sample, but as long as he thinks it's representative of the typical traffic and the speeds that they go through, then it should be okay. All right, just use that as a caveat whenever you publish your results. Just say that, how you gather data, be forthright about how you did it. Independent. So apparently he was only looking at the lead car. So if there were 2 cars stacked, in one in front of the other one, the radar would only detect the first car, not the second one. And so he really only had the lead car. Could that be an issue? Well, the lead car might be the lead car, because if you're not first, you're last, right? So name that movie. So they might be going faster than the car that's behind them, right? That's tailing them. Or maybe the person behind them is pushing them to go faster and tailgating, stuff like that. So anyway, that could kind of mess with our results. So it's not actually truly independent. Also, we're sampling without replacement, and we're only sampling the lead car. So we might have some issues there. So again, we would make sure that we told people our method when we publish the results. We're also sampling without replacement, but as long as we're sampling less than 10% of the population, which we obviously are, less than 10% of the people that drive through in 15 minutes, right? Definitely, it's going to be less than 10% of all the people that drive through in any given day. So the last one is nearly normal. We want to know, do we expect the population to be normal? Well, we have to look at a histogram for that, and he graphed it out. The sample itself looks nearly normal, which leads us to believe that the population it's being drawn from is probably nearly normal as well. So just like heights or waist size and stuff like that, even though that would be slightly skewed. But in this case, the data looks like it might be slightly skewed to the left because we might have some people who are going really, really slow, but no one's going to be like, doubling up the speed limit or anything like that, flying through at 60. So it looks nearly normal. The question isn't, is a sample normal or nearly normal? Do we believe from the sample that which the sample is representing the population, do we believe the population is nearly normal? Or is it nearly normal enough? So depending on our sample size, the central limit theorem will kick in. With a sample size of 23, even if the data was skewed or multimodal or something like that, with a sample size of 23, the average that we get from that will actually follow the sampling distribution model will actually follow a normal model. And so we really, unless it's like heavily skewed like CEO data, then we would need like 200. We've seen examples where this will actually work just fine with the central limit theorem kicking in. So all of those are good. We just mentioned our caveat with how we gather the data. All right, so the sample, the average, if we actually put all that data in the calculator, the book does it for us, so I didn't even bother. But you'll have one like it on the assignment, so make sure you do that. It tells us an average speed of 31 miles an hour, which is slightly over the posted 30 mile an hour, but is it statistically significant, that 1 mile an hour increase for the average for a sample size that big? That's the question we're trying to answer. Standard deviation for the speeds was 4.25, so that's a fairly large standard deviation for the sample. We want to create a confidence interval, 90% confidence interval. Also, we have a sample size of 23, so 22 degrees of freedom. We are using a t distribution because we have to kind of adjust our model for the fact that we are sampling with means, and we're basing the standard deviations of the means and their deviations from the sample's mean and not the population's mean. Just like Gossett found out with his alcoholic beverages, sampling only 4 with 3 degrees of freedom, he had 3 times the amount of false positives, which told him his model that he was using was flatter than the actual standard normal model that we always assumed before that is what we would use with means, especially with small samples. All right, so let's find the standard error for our sampling distribution model. That's going to be the standard deviation divided by the square root of n, which I'll just save you time. We'll put that in the calculator. We get 0.886. So one standard deviation above that is obviously going to be just a little bit of a t-score, like a z-score, but a little bit over 1. So this might, I haven't even created the confidence interval, but I don't think this would be a statistically significant observation because it's only 1 standard deviation or standard error above. Oh, it's so much fun to say. 1 standard deviation above the mean, the sample mean. Or the sample mean is only 1 standard deviation above what we'd expect, centered at 30. So to find our confidence interval, we can put that in the calculator. First, we need to find the t-score to find out, or t-star to find out how many standard deviations we need to go over. So with 90% confidence, we're going to do second distributions. We're doing an inverse t model, which is the 4th option. We want 90% confidence, so that's going to be 5% on each tail. So we can either do 5% or 95%. That'll give us what we're looking for. Degrees of freedom are 22. And that gives us a critical value of 1.717 standard deviations that we have to go out for our margin of error. Excuse me. So we can put this in our calculator and it'll do all the work for us. Otherwise, we multiply that times the standard error and add and subtract it from our sample mean. So I'm going to go from stat, go over to test, and we're not doing a test, we're actually doing an interval. And it's not the z interval because we don't have the population parameter, because we don't know what the true standard deviation and mean speed is. We're trying to estimate the population mean. So instead we're using a t interval, which reminds us that it's based off of inferences for means, and we don't have the actual data, but if we did, we could put that in, but they gave us the summary statistics. So that was a mean, I think, of 31. Yeah, so average, sample average of 31 with standard deviation of 4.25, which is a fairly large standard deviation for the sample. Sample size of 23, confidence level, we're going to do 90%. I'm just going to delete that and hit calculate. So that gives us a confidence interval anywhere from 29 to 32%. So interpreting that, if we're kind of basing a test off that, we notice that 30 miles an hour is contained within that confidence interval. So we are 90% confident that the true mean of the true average speed of the people passing through, at least in those 15 minutes, at that time of day, I guess is how I would probably say it, is somewhere between 29.5 and 32.5. So it's possible that they were speeding, but the average person was speeding, but we do not have enough data in order to reject the null hypothesis. So if we use the interval to test it, because 30 is contained in the interval, we don't have enough evidence to reject that claim. All right, so our confidence interval is right there. We also would say a caveat that it was not a random sample of vehicles. It was a convenient sample taken at one time on one day, and the participants were not blinded. So drivers could see their speed in the radar, and some may have slowed down like I would have done. Of course, that's why they put those up there. So I'm reluctant to extend this inference to other situations and to claim that. So we do need to be careful about extrapolating out to the rest of the population. All right, so do we have enough evidence to say that the mean speed is above 30? So we could test that, and we did with our confidence interval. When we did our confidence interval, it was 90% confidence, which meant that as long as we weren't doing a two-sided test, which we really were only interested in one side, is that if it was greater, I mean, there'd be a 5% alpha level because there's 5% on one of the tails of 90%. So with a confidence level of with a statistically significance alpha level, right, of 5%, we would not have reached that 5% significance level in order for us to be able to reject a null. So we would have failed to do that. But what if we do this again with the confidence level of only 10%, because this is not super critical, then will we have enough evidence to reject the mean? So we're going to set our alpha level allowing 10% false positives. So that'll give us the critical value with that one. So our null hypothesis is that the mean is 30. The average speed of the cars passing through the neighborhood is 30 miles an hour. Our alternative is one-sided with only greater than. So we're only interested if they're speeding, not if the average is going to be lower than 30. That would be totally acceptable. To find the standard error for the sampling distribution model, which is going to be based off of the assumption that it's true, right? The null is true. That's how we calculate our p-values. We plug in the standard deviation of the sample and the sample size of 23, which gives us the same value we had with the confidence interval. And then we can find the t-value, like a z-score, but a t-score, by taking the sample mean minus the hypothesized mean divided by the standard error of our sampling distribution model, which is going to be a little bit over 1 standard deviation above, or a little bit less. Yeah, a little bit over 1. So if we see, that's actually going to be right about there, between the two values there. So that would be within that 10% alpha level. But if we set our alpha level back to 5%, now this is no longer statistically significant, which tells us that our p-value is somewhere between 5 and 10%, which we'll calculate in with the calculator pretty soon. All right, so critical value using this would tell us that it was 1.13 standard deviations above the mean. That can't be quite right. What did I do? Yeah, 31 minus 30 divided by standard deviation. Okay, so yeah, it is 1.13 standard deviations above the mean. Let's go ahead and calculate what that value would be. So let me hit, I'm going to do that again. So we have stat. We're going to do a test. We're doing a t-test because we don't know the population parameters, so we can't use a normal model. That's what the z is all about. We have the summary statistics, so the hypothesized mean. So we're going to say the hypothesized mean was 30. Our sample is actually 31. Sample size, we want to know if it's larger, not smaller, or two-sided. Hit calculate. All right, so this gives us a p-value. So what did I do wrong? Oh, okay, this is 1 standard deviation here. So the 31 is actually going to be on the other side of the 10%, okay? So let me pull this back up. That's what I did wrong, because it was only 1.13 standard deviations above. That gives us a p-value of 13.5%, which is not less than our 10% alpha level. And we never really use alpha levels that are less stringent or less strict than 10%. That's the lowest we usually go to, even when we're talking about candy. So at this point with this particular sample, we did not have enough evidence. And again, we would state our caveat that it was not a random sample, and the fact that we didn't have they had the radar, and we only recorded the lead person, which might bias it in one direction. And because they saw their speeds, even people who typically would speed, they might have slowed down. as such was the confession of a certain teacher that I heard of once. I don't know. It's okay. Or is it? So next question we have, which is like yesterday's assignment that I posted. It says, what value of n, or what sample size, would yield 95% confidence level with a precision of a margin of error of only 1 mile an hour? So if we wanted a 95% confidence, which is more confidence and more precision of only 1 mile an hour, the plus or minus for the margin of error, what would that take? So from our formula, we know the margin of error is going to be the critical value, t star, times the standard deviation divided by the square root of n, which is our standard error, right? So to get that t star, we have to use, well, the problem here is we notice that both the t star and this has n involved in the formula, right? So to get this from the calculator from our technology, we have to know what the value of n is. Well, we're trying to solve for n, the sample size, so we can't do both at the same time. So if you remember from yesterday, what we do is we take the worst case scenario, or which would be using a normal model, which would be the smallest possible sample size we would need. And then once we use the z-star values from the normal model to get an estimate, we replug in that estimate using the critical value. So let me show you how that works. So if we want 95% confidence, if you remember the critical value, that's going to be 1.96. I'm going to show that real quick. 95 z-star from inverse normal is 1.96. All right, so 1.96 times the standard deviation divided by n. So all we have to do is divide the 1 by 1.96. Which I'll put this in the calculator. So we have 1 divided by 1.96. And then we're going to actually, because n square root of n is on the bottom, we switch the order of the numerator and denominator across the equal sign. Because we're just multiplying both sides by radical n, and then dividing both sides by whatever that value is, the 51%. So essentially what we end up with is 4.25 divided by, and I'll put it in as a fraction so you can see better, alpha x. So that divided by our previous answer, so it's going to be second ans. And remember, this is what n squared is going to be equal to. So in order to find out what n is equal to, we simply square it. So take that value and square it, which gives us an approximated sample size of 69. So we need to sample 69 cars in order to have the confidence of 95% with a precision of 1 mile an hour for our margin of error for our confidence interval. So now this is the best case scenario if we were able to use a normal model, which we can't because we don't know the actual population parameters. This is what we're trying to estimate. So we would actually round up from 69 to 70, because we can't have a fraction of a person. And so in order to be guaranteed that we are less than 1, we would need to go up to 69. Now that we have 69, we can actually find our t-star value. We do that from going to, second distribution, going down to the inverse t model. We want an area 95% confidence, so I'm going to do 2.5% on both sides, so that'll be that value. Degrees of freedom, we said that would be 60. Okay, sample size is 69, so degrees of freedom would be 68. Did I do that right? Is that actually 69? Or would it be 70? I think I typed that in wrong. Let me quit out of this real quick. It was 69, so we would actually have to go up to 70. Alrighty. We all make mistakes. We all have those days. All right, so where was I? Okay, stat. Hopefully it saved what I had. Not stat test. We're going to go distribution, inverse t model, whatever. 0.975 degrees of freedom. We're going to have 69 degrees of freedom because it's 1 less than our sample size, which gives us a critical value of 1.995. And then we can plug that into our formula. Oh, I just didn't do the same thing. So originally we used the 1.96 for the z-star, but now we have to do the same thing, and we're going to replace our math using the updated value. Notice it's not much different. Well, 3% different. That's quite a bit, but anyway, not much more different than this. But when we do update it, we get 72 as our estimated sample size to get this amount of confidence with this amount of precision, which is too higher than what we originally would. So that would be the proper method. All right, so if you guys look out your assignment, we'll go through the first example together. It's kind of a fun one. So a herpetologist, which is snake specialist, found a certain species of reticulated python that have an average length of 20.5 feet with standard deviation of 2.3 feet. So what did they just give us? So there's a certain species of python, and they say that the average length for all of those python and the standard deviation for all the python was given. Those were not sample statistics, those were population parameters. So this is a little different than what we've been doing in this chapter. We actually have to go back to chapter 17 when we actually knew that information. And when we knew that, we don't have to use a t-distribution. We can actually use a normal model because we know the population mean to compare our sample to calculate our standard deviation off of. So we don't have to use t-distributions to correct for the fact that samples are always going to vary and have less deviation from their own sample means instead of the population mean. So scientists collect a random sample of 30 adult pythons to measure their lengths. The sample, so now we have a sample statistics here. They don't give us a standard deviation for the sample because we don't need it, but we do have the actual mean from that one. So the sample mean was 19.5 feet long, which is a foot less than the average that we would expect. So one of the herpetologists fears that pollution might be affecting the natural growth, so stunting their growth because it was an average, it was a foot less than what we expected, the natural growth of the pythons. Do you think the sample result is unusually small? So that's the question we're always asking. Is this sample statistically significant to suggest that there's a change in what we expect? Is this a deviation from the natural growth, or could this have just occurred by natural sample variation? That's always the question we're trying to answer with inferential statistics. So what model should we use? We're using a normal model or a t-distribution. Now, typically we're talking about mean, so we would think t-distribution, but this one is special. Why is this case special? It's a very rare case because we know the population parameters. We almost never know the true population parameters, and we're trying to estimate those. But in this case, they believe they know the true population parameters, which just came from a different sample. I just completed my census today, so maybe we do know from the census that we send out to all the reticulated python what the average and standard deviation are for the entire population, possibly. All right, so check your assumptions. Is this a random sample? Did they tell us it was? No, but we're assuming that they did a random sample, but that could be an issue. So we would just state a caveat. We weren't sure how the data was collected, so they could have only targeted areas where there were young adult pythons, and they perhaps weren't fully developed, and so they had shorter ones than possible. So depending on the areas that they targeted, they could have some issues, right? Independence. We're sampling without replacement, but we can override that with a 10% condition. So it's not truly independent because there's more than 300 pythons in the population, we're good to go. We're all Gucci. Nearly normal condition. We're not talking about the sample being nearly normal, but from the sample, do we believe that the population is nearly normal, or is the sample size large enough for the central limit theorem to kick in and to correct the population being not nearly normal, whether it's bimodal, multimodal, unimodal, heavily skewed with outliers, something like that. With a sample size of 30, that's pretty large. As long as there's not some crazy outliers or really skewed population, we should be fine. And we're talking about adult pythons, so I doubt that it would be. I would expect it to be nearly normal. And so we shouldn't have any issues at all. But even if it wasn't, with such a large sample, central limit theorem is going to kick in, and our means for a large sample of 30 should be nearly normal or normally distributed by a sampling distribution model. So find the parameters. Well, in this case, we have our mu and sigma. I'm using Greek letters for the parameters, not Latin ones, which would be the ones we're used to of y and s. The reason we're using Greek is because Greek comes before Latin, right? The Latin language is actually based off of the Greek culture, the Hellenistic culture. So the Greek parameters, Greek letters for the parameters, and the samples that follow from those parameters. So we have the population parameters, which allows us to use sampling distribution models from chapter 17, which is rare. So notice here I'm using the standard deviation and not the standard error because this comes not from the sample, but this comes from the sigma, which is the actual population. So if we know the population parameter, we know how much a sample of 30s mean. A mean of a sample of 30 should vary if the true mean was 20.5 feet. So here's our sampling distribution model with the sample size of 30. Now notice I'm not mentioning the degrees of freedom. That's kind of cluing you into the fact that this is a normal model, not a Gaussian distribution of the family of models there. So this is going to be centered at 20.5. That's what we expect with a standard deviation, which we would get from, put it in the calculator. I'll just save you time. So 0.42 feet. So I kind of graph that out. So if you want to fill in those values, I'm sure you can pause the video. Next thing we want to do is calculate the z-score for our observation. So where's 19.5? Well, it's going to be a little bit more than 2 standard deviations below the mean, which we would generally consider to be statistically significant and an unusual observation for a sample mean. So to find the actual z-score, we subtract the observation minus the mean, which is -1, divided by the standard deviation for our sampling distribution model, which is going to leave us with it's 2.38 standard deviations below the mean. So is our observation statistically significant, or would you believe that it may be due to random sample variation? Well, we can actually find the actual p-value if we want. Multiple ways to do that since we just found the z-score. One easy way to do it would be to do from the normal CDF, because we are using a normal model. Cumulative density function from negative infinity to a negative, I have to make sure I put this in as a negative instead of subtraction, but negative 2.38. We are using z-scores, so that's the standard normal. Gives us a p-value of less than 1%. So even if we said a very strict alpha or significance level of 1%, this would still be a statistically significant observation for a sample size, for a mean of a sample of 30 snakes. So does that mean that the herpetologist was right and that it's pollution that's causing the stunted growth? No, not necessarily. Again, it wasn't a random sample, so they could have just been targeting, I don't know, like a snake mall where a lot of teenage snakes like to hang out or something like that. So I don't know. We would have some caution in that. We would put a caveat with that. Also, yeah, just put a caveat. So we're not entirely sure about that, but this does seem to be an unusual thing. And correlation is not equal causation. We'd have to do an experiment where some of them are exposed to the pollution and contaminants or whatever, and some were not. But just like the liver failure with the dogs, there's ethical issues with that, right? If we think that pollution is bad for the snakes, we're not going to purposely shorten the lifespan and the length of these snakes. Okay, that would be kind of cruel. So is it unusually, is it statistically significant? Yes, in general, because it's more than 2 standard deviations. But whenever we looked at the actual z-score or p-value, we were able to get less than 1%. Another way we could put this in the calculator, and I'll go ahead and show you that, is going to stat test. Now we are doing a test here. Typically we do a t-test, but that's based on t models. Now we can actually do a z-test based on normal models because we have the actual population parameters. So we're hypothesizing that the length is 20.5 with the standard deviation for the population. And notice that they're using the mu and sigma. See, this is hinting you that that's the population values. And that's the only reason why we're able to use a z-test instead of a t-test. So that's going to be 2.3. So that's our mean and standard deviation parameters from our population. Our sample, which is the x bar, is going to give us 19.5. And notice on this one, they don't even ask us about the standard deviation of the sample because it actually doesn't matter. Okay, sample size in this case we said was 30, and we want to know strictly if it's greater than, or sorry, less than that. So if it's stunting the growth, not accelerating the growth. So this would be a one-sided test. Hit calculate. You could argue that a two-sided test would be interesting if they were accelerating growth as well, which would actually double our p-value and make it more than 1%. But anyway, and notice we got the exact same values that we did with the other one, even though the z-score here, this value was rounded, so we wouldn't expect it to match exactly, but it's close enough. All right, so good job. Right under 30 minutes, so we did it. I'm going to go ahead and end the video. Make sure you guys, as I said earlier, make sure you're uploading the assignments to Google Classroom so that I can track and make sure you guys are staying caught up and keep you accountable. And if we are falling behind on the assignments, I know there's a lot of reasons why in these crazy times that you guys might be falling behind. I know there's a very contagious disease going out around, highly infectious and contagious called senioritis. And so just trying to keep you guys from just totally falling off and only getting 75% of the education you were supposed to get this year. So trying to hold you guys accountable, stay strong. The last day for you guys is May 8th. And I know you seniors, you're so ready to graduate, but let's finish strong. Let's not finish the last lap at all. So anyway, this is good for you, and you can thank me later, even though it's a lot more work for me and for you. But this is good stuff, and it's important to know if you're going to get college credit and save yourself potentially thousands of dollars and having to pay for tuition and fees at a four-year university. You can come back and thank me for that later. So anyway, I hope you guys are having a good time, and that your families are healthy. And I miss seeing you guys in class, and I'm glad I can do these videos and still teach you the rest of the content. But I really wish and prefer that I could do this in person so I could see your face and answer your questions and stuff like that. So anyway, thanks for hanging in there. And for the few people who were watching the videos every day, thank you for your honesty and your character. So I don't even know who you are, but there's a special place in my heart for you, doing the right thing, even though there was no way of tracking it. That's amazing, and you'll be rewarded for that. So, but that's not up to me. So anyway, see you guys. Have a good day.